Okay, so the first question that was asked was chapter 22, number 55. In this question, we had a wire that was carrying current I1. And then this, yeah. So it's being recorded right now, and then I'll upload it after we're done. Okay. So then we also have next to this wire a loop of wire that has current going counterclockwise through it. We can label each parts of these wires. One, we'll layer this bottom one, wire number 2, wire number 3, and wire number 4. They give us a couple other things in the problem, in the text of the problem. They tell us that the top wire is 0.075 meters away, and this bottom one is 0.175 meters away. They also give it that the currents, I believe it's I1 is 30, and the current through this bottom wire, this loop, is 15. And they give us that the dimensions of this guy in the horizontal are 0.3 meters. That's completely unreadable. 0.3 meters. That's not much more readable than the other. Okay. And what they want us to do is calculate what the total force is acting on this wire. So we have current flowing. Anytime we have current flowing inside of wires, they're going to be either attracted to each other or repelled from each other. So something's going to happen with these wires. In the top wire, are they traveling in the same direction or opposite directions, the current?
Opposite.
So I1 is going to the right, I in this top wire piece is going to the left. So the currents are going opposite directions. Are they going to attract or repel? They repel. Opposite directions for currents will repel. This is different than charges, right? Opposite charges attract, opposite currents repel. So this current, the current that's going through this upper wire, it feels a force that's going to push it down. I'm just going to call that F1. That's because the currents are going in opposite directions. Now how about this bottom wire? That's going to the right. The top wire is going to the right. They're going the same direction.
Yeah.
So this bottom one's going to be attracted. So it's going to feel a force pushing it up. That's F2. That gets a little weird, and answering this question completely kind of requires you to know the calculus definitions of physics. Your algebra-based class, right?
Yeah.
Okay, so you have to just take my word for it. That wire number 3 and wire number 4, notice they're going in opposite directions. So the forces they experience, this one's going to experience a force that's opposite to this one. Yep. So they're going to end up canceling each other out. Because if we look at the force that we feel between two wires, they give us this equation in the book. The force per unit length is equal to mu naught times I1 times I2 divided by 2 times pi times r times L. What are all these things? What is mu naught? Sorry, there's I made a little right mistake there. Force per unit length, mu naught I1 I2 over 2 pi r. No. So mu naught, what's mu naught? permittivity of free space. 4 pi times 10 to the negative 7. It's constant. I1, what is that? Current 1, I2.
Current 2.
Current 2 divided by 2.
2.
2. Pi?
Pi.
Pi. R. What is R?
Radius.
Radius. What does that mean? I don't see any circles up there. The radius here is the distance you are from the wires. The distance between the wires. So, wire number 1. Wire number 1 is one distance from the wire, 0.075. Yeah? It's traveling opposite in direction to wire number 2. Wire number 2 is 0.175 meters away. So these are going to be 2 different force per unit lengths. The radii are different. Yeah? Everything else is the same. U naught, I1, I2, 2 pi, all that's the same. The radius has changed. So I got 2 different forces, one from upper, one from below. Now I look at the wires on the side. Wires on the side, I can imagine this little point on this wire is going to create a force, and so is a point a little bit below that one, a little bit below that one. All of these are going to create their own little forces. I can use calculus to sum these up very easily, but we don't need to do that because we have each little point down here is going to create a force in one direction. Each little point over here is going to create the force going the opposite direction. Right? So they're going to cancel each other out. So the side wires, they don't matter. We don't have to worry about the side wires at all. Okay, so that's why they cancel out. Now if I want to find the force, I need to actually calculate what the forces are. I need to solve this for force. How do I get F by itself? Multiplied by L. So I multiply by L over. So force is mu naught times I1 times I2 times L divided by 2 times pi times R. Where L is the length of the wires that are in common. So this wire is really, really long. But the only part of the wire that's going to put a force onto these wires are the parts of the lengths that are in common between the two. So just this little chunk of the wire that's the same length as that little chunk.
So 0.3 meters?
0.3 meters is your L. So if I'm going to calculate these, if I'm going to calculate F1, F1 is mu naught, which is 4 pi times 10 to the negative 7. Times I1. What was I1? I1 is 30. What's I2? 15. What's L? 0.3 divided by 2 times pi times R. What's R? 0.075. It's the distance I am from that top wire, distance between my 2 wires. And then what direction is this force going? F1, where is it going? Down. So what do we need to add to the front of it? Negative, because it's going in the negative y direction. So you plug in all these numbers, plug them into your calculators, and you should find negative 3.6 times 10 to the negative 4 newtons. And then we repeat that process for F2. F2 is mu naught, which is 4 pi times 10 to the negative 7, times the currents, 30, times 15, times the length that's in common, 0.3, divided by 2, times pi, times the radius. How far is the bottom wire? 0.175. And that, when you multiply all your numbers out, is going to be 1.54 times 10 to the negative 4. Do I need a negative in front of that one?
No.
Why not?
Pointing up.
Because it's pointing up. So if I then want the total force, F total is going to be F2 plus F1, where F2 is 1.54 times 10 to the negative 4 newtons, and then plus F1, which is plus the negative 3.6 times 10 to the negative 4.
So your total force is 2.06 times 10 to the negative 4 newtons.
Yeah. Any questions on that? Yeah, yeah, it'll be negative. Because it's going down.
Is that one negative in the beginning? That's going down?
Yeah. We pop that negative in there because it's going down. Good. Any other questions on this one before we move to the next one? It depends on what directions they're pointing. So if they were going the same direction, they would both be positive. If they're going opposite directions, you subtract the two. Yeah.
How many points are on the top?
That'd be a 10-point question, probably. Yeah.
You said the opposite currents repel?
Opposite currents repel.
So the same.
Same attract. So I1 is pulling these currents, pushing this one down. But then, what is this one doing to I1? What would the force of this one on this one be? What direction would this one go? It would be pushed up. So they have equal and opposite forces. Whose law is that? Newton's. Which one? Newton's third. Ah. Hear that, YouTube? They learned. That was physics 1. Like, subscribe, share. Click that little bell. No, I don't want their comments. Yeah.
So for the forces, these different R's.
Yeah.
Why?
So if I look, the force to R is the distance you are from this wire. So the top wire is 0.075. The bottom wire is further away, 0.175. Yep. We got anything else? Anything else? No? All right, the next question we want to do is number 27 in chapter 23. This is the one where we have a uniform magnetic field, where the magnetic field is pointing out of the page throughout this whole little rectangular region. And then we have a bunch of coils of wire. Coil A. Let's do the coils in a different color. Coil A. Coil B. Coil C, coil D, and coil E. Okay. So what this question asks is, as I'm moving this coil through the magnetic field, the field is uniform inside the rectangle and 0 outside. So there's no magnetic field on the outside. We want to know the direction of the induced current and the direction of the induced magnetic field on each of these coils. Yeah?
I don't know this. Like, we went over this problem.
Yeah, I don't know. It was specifically asked to see it again. Yeah. I think in class I did it on the whiteboard. A couple people have things in their notes that they don't know what they mean.
Oh.
So we'll do it again. Okay, so I've got this coil. The important thing with induction, you only get induction when the magnetic field that something is inside of changes. If there's no change in the magnetic field, there's no induction. So you got to imagine taking these little coils and moving it a little bit to the left and a little bit to the right and see if the magnetic field that they're inside of changes. And if it does, that actually determines that something's going to happen. So let's take my little coil. Here's my coil. I'm going to induce current in my slinky, make it electric. If I move this coil a little bit to the left, is there a magnetic field? A little bit to the right, is there a magnetic field? Is anything changing at point A? No. So is there any induction? No, nothing's happening, so we don't care about A. How about at B? Is something changing? If I move it a little bit to the left, what magnetic field is inside this coil? There's no magnetic field. It's outside. I start to move in. Is there a magnetic field in the coil now?
Yes.
Yes. Is it happy about that? No. What does it want to do? It wants to stay the same. It has zero magnetic field, and then it goes to having a magnetic field. What direction is the magnetic field that it ends up getting by moving into this? What magnetic field is inside of the coil? You get a magnetic field coming out.
So we have a little magnetic field by entering inside of here that's coming out. Little circle with a dot.
Induction doesn't like that. Induction wants to go back to the way things were when it had no magnetic field. So how does it create no magnetic field? What does it have to do? You've got one coming out, so how does it cancel out the one going out? It creates one going in.
So we're going to induce a magnetic field that goes into the board.
So the yellow is the direction of induction. Okay? Now I have to figure out what direction is the current in this loop going to go to create that magnetic field. Induction is all about changes in magnetic fields creating currents that create new magnetic fields. So to figure that out, I use the second right-hand rule. There's multiple versions of this. Some of you have went over different versions that I've never heard of, but they work, so you can use those. The one I tend to use, I take my thumb and I put it in the direction the current's going. I take my fingers and I point them to where I want the magnetic field, and then I bend them, and that gives me the direction of my magnetic field. When I'm doing these, if I have a loop, I guess. I have no idea what the answer is. I just say, I can go in one of two directions. What are the two directions I can go around that loop? I can go clockwise or counterclockwise. What do you want to guess? Clockwise?
Clockwise is what I heard, so we'll guess clockwise.
I just picked the bottom of the loop. I could have picked any point on that loop. It doesn't matter. So I take my thumb and I put it in the direction the current's going. Take my thumb, point it to the left. I take my fingers and I point them to where I want the magnetic field. I want to know the magnetic field. Do I want to know above or below this little arrow that I've drawn? Above, because that's where the little X is. That puts me into the middle of this loop. So I point my fingers up. I bend my fingers. What direction are they going? Into the board. Is that what I want? Yes. Did I get the right answer? Yay.
So it's going to be induced current
Goes clockwise. Induced magnetic field goes into the board. How about part C, point C? If I take this little loop and I move it a little bit to the left, is the magnetic field changing? No. If I move it a little bit to the right, nothing's changing. Still the same magnetic field. So do I have any induction at point C?
no induction.
What was that? Hand roll for B. So I picked this point to show something going clockwise. So I take my thumb and I put it in the direction that the current's going. I take my fingers and I either point them above or below, depending on where I want to know the magnetic field. I don't care about the magnetic field down here, because that's not inside of the loop. I want to know the magnetic field in the loop. I want to stay in the loop. So I got to point my fingers up to be inside of the loop. And then when I bend them, they go into the board. Okay. And that represents the induced magnetic field. That's the X right there. The X-Men logo. Everybody seen the preview for the new X-Men movie? Oh, it looks horrible. Skip it. It's This weekend, Captain Marvel. Anybody going to Captain Marvel this weekend? Did you get your tickets yet? I got my tickets. Tickets, multiples. I'm going with someone. Poor girlfriend. Should pay her. You can offer your condolences on the video. Yeah, Carrie.
Direction of induction and induced magnetic field are both into the page.
The induced magnetic field is into the page. The induced current is counterclockwise.
Oh, induced. What was it in the page again?
Induced magnetic field.
Into the page. Okay. And the direction of the current is
Clockwise.
Is it
And we'll see it. We'll do it again with part D. Okay. Any other questions here? All right. Let's look at part D. Part D, we have my loop. Here's my loop. If I move it a little bit to the left, I'm inside of the magnetic field. If I move it a little bit to the right, I'm outside of it. So the magnetic field goes away. Is there something changing?
Yes.
Yeah. Is it happy about it?
No.
No. So I'm going from having a magnetic field. In what direction is the magnetic field going? Out of the board to what do I have if I leave? I have none. So I go from out of the board to no magnetic field. Yep. What do I want to get back to once I'm outside of this? I want to be back to having a magnetic field pointing out. So what direction is my induced magnetic field going to go? It's going to go out. So my induced magnetic field, and we'll keep a consistent color, is going to go out of the board. How do I get a magnetic field pointing out of the board? What direction does my current have to go? Counterclockwise. How do we know that? Because the other one was clockwise. Or we can use the second right-hand rule again. So I picked a different point on the circle. Instead of being at the bottom of the circle, I went to the right of the circle. To the right edge. So I take my thumb and I put it in the direction that the current's going. Over here, my current's going up. If I want to be inside of that loop, I can point my fingers either to the left or to the right. What direction do I have to point my fingers to be inside of the loop? I have to point my fingers to the left. And then I bend them. What direction are they going? They're coming out of the board. Is that what I want? Yeah, so there we go. Okay.
How do you know which way the current's going? Is it just whichever you choose?
You guess.
Yes.
So I guessed that it was going this way. I got out of the board. If I had guessed wrong, what would I have gotten? Into the board. That would be the wrong answer, right? Because I want the magnetic field to come out. So I would know I guessed the wrong thing, I need to pick the other one. Yes?
So is in always clockwise and out always counterclockwise, or is that just for this particular?
I think in is always clockwise and out is always counterclockwise. I think so.
What if you were to put the dot at the bottom of that circle? Would it change? Like you get on.
If I put the arrow down here,
Yeah, would it change your answer?
let's put the arrow down there. Let's see. Let me draw a big loop. And I want the magnetic field to come out.
Out, and then your point is on top.
And you want down here? So there's my arrow. Still going counterclockwise. So take my thumb. Thumb goes in the direction that the current's going. So my thumb's going that way. I take my fingers. Do I point them up or do I point them down? Point them up. I bend my fingers. What direction are they going? Out of the board. Still works. Doesn't matter where you pick. If I pick the top of the circle. So I keep going around and going counterclockwise. Pick the top of the circle. Go this way. Take my thumb. Going this way. Do I point my fingers up or do I point them down? I point them down. I bend my fingers. Where are they going? Out of the board. Same answer. Okay? I'm going to injure your shoulders. Okay. Any questions?
Can we use this little guy for that?
No.
This is the first right hand rule?
That's the first right hand rule.
Second.
This is the second.
So you point your fingers above or below the magnetic field that's given.
Above or below the current. Or left or right of the current. Depends on where you draw. Okay? And then we go to the very last one. Point E. If I move it a little bit to the left, nothing. Point it a little to the right, nothing. So is there any induction in point E?
No.
No. So do we care about point E? No. Yeah, this would be 10 points. Yeah, Carrie.
If you were to flip the whatchamacallit's coming out in the square, the magnetic
This, if I would make this going in,
going in, would it flip D and B? Is that all it would do?
Yeah. Okay. Any other questions on this one? No?
Okay.